Okay, so today we have the last of our fields that we have to introduce. It's the Dirac field. And so you have to do a quick review of what the Dirac field is, a couple of useful identities, etc. So this is, of course, the field for a fermion. It's given the symbol psi. There's generally not written, but there's an index on it which runs from 1 to 4, so there's 4 components to it. And so you tend to think of it like a column vector. These 4 components. What this means in the long run is that almost everything we do with this field is either a vector or a matrix. And our notation is such that you never see that stuff. So the biggest technical issue is putting things in the right order and doing all the right stuff with the matrix indices. Anyway, where did it go? Oh no. Just a sec. All right, well, I'll find it later. So the Dirac equation is the following form. It's I, so gamma mu derivative mu, so it's a common sum over those 4 components, minus m psi equals 0. So these gammas here are 4 by 4 Hermitian matrices. And their form is the following. I'll use the standard basis. Gamma 0 is 1, minus 1, 0 on the diagonals. So each of those 1s is a 2 by 2 1. Okay, so it's 4 by 4, 2 by 2 1s there. And gamma vector, gamma I, is sigma I up there, 0, minus sigma I there, 0. And these satisfy anti-commutation relations. Gamma mu, gamma nu anti-commuter is 2 g mu nu. So if you take gamma 0 and square it, that's 1. Because gamma 0 plus gamma 0 is 2 times g0, 0, so that's 1. Okay, that's the main one. Gamma I squared, if you just multiply it out, of course this one's obvious. Gamma 0 squared is 1. If you just square that, you get 1. Okay. The notation that we'll adopt is that if you write gamma mu d mu, we'll tend to write that as d slash, and anything slash, a slash, is gamma mu a mu. So instead of having to write all those gamma matrices. But anytime you see that slash, again, you're seeing a matrix. Okay, so in that notation, the Dirac equation is I d slash minus m psi, and it's said just like I said it there, d slash or del slash. Okay, the Lagrangian. Actually, I need one more thing before the Lagrangian. Let's see if I can squeeze it up here. It's the definition of psi bar is psi dagger gamma 0. So if psi is a column vector, psi bar is then a row vector, and so you multiply it from the right with gamma 0, it's still a row vector. Okay, so this is, something like psi star 1, psi star 2, psi star 3, psi star 4 times the matrix gamma 0. Okay. Now, to explain why that comes in so heavily, I'd have to do some work that I'm not particularly interested in doing right now. But it just be said that it's the one that satisfies the Dirac equation, which we'll see conjugated. Okay, so the Lagrangian is psi bar I d slash minus m psi. And this derivative in the Lagrangian, you could write it as in its Hermitian form. And if I was, is d slash with the derivative acting that way minus d slash with the derivative acting that way. So the Hermitian conjugate of this d slash is derivative acting the other way. So I'll use that for my next statement. Okay. So, or I could, this would be written as I over 2 d slash left right. That's what that means. Okay. So, if you then vary, so you take if I take the equation of motion d mu, the variation of Lagrangian with respect to d mu psi bar minus the variation of the Lagrangian with respect to psi bar. It's easiest in the form where I don't use the Hermitian form. Let's do this where the derivative is acting that way. The equation of motion just turns into then the Dirac equation, I d slash minus m psi equals 0. And the other one, if I do the same thing with psi d mu, actually, sorry, anyone see the mistake there? I have a mistake. The bracket's in the wrong place. That guy should not be there. It should be right here. Everyone. So if I do the same thing, with the varying psi, you get the conjugate equation, which is minus I d slash acting that way minus m. So it's just the Hermitian conjugate of the whole thing. Okay, plugging away. Any questions? Plugging away, the Hamiltonian. Well, so pi bar is the variation of the Lagrangian with respect to d0 psi bar. Well, that would be minus I over 2 gamma 0 psi, right? So d0 psi bar sits right there, the time derivative, so there's the gamma 0, the minus I over 2 gamma 0. I get that. Pi is d0 psi is plus I over 2 psi bar gamma 0. Okay. And then the classical field theory tells us that we form the Hamiltonian. The Hamiltonian density then would be pi d0 psi plus pi, well, let me put it in the right order. It's d0 psi bar pi bar minus Lagrangian. Okay, and the I don't know if you can see, I could, if I take, let's look at this guy here. The pi is psi bar gamma 0 times d0 psi, okay, is just like the I over 2 piece d0 gamma 0 that sits right there. So the linear pieces cancel off. The time pieces cancel off there. Let me write out the answer and see if you can see how it might come about. Okay, so it's the spatial pieces minus I gamma dot del plus m psi. Okay, so the time pieces cancel. This pi d0 psi, with this being pi, cancels off the time derivative piece from the Lagrangian, and you're then just left with the space derivative pieces in the Lagrangian. Okay, so there's your Hamiltonian. This is often written in the following form. No point in doing it here, but if you've seen it before, it's minus alpha dot del plus beta m psi. So what I've done is I've just taken that psi bar and made explicit the gamma 0. So beta is just gamma 0, and alpha is gamma 0 gamma I. Okay. As I say, there's no particular point for us to do that here, but that's conventional notation when you first see the Dirac equation. Okay. Okay, so we now step through the usual procedures for finding a field and quantizing it. We look at the solutions. I'm assuming that you've seen these before, so I'll be quick on them. But we can look for solutions. Psi of x is of the form e to the minus I p dot x u of p. Then the Dirac equation I d slash minus m psi equals 0 turns into p slash minus m u of p equals 0. So that's a matrix equation, because that's p slash is a matrix. And the solutions end up being some normalization, so u of p is, okay, so leave a space, follow me in leaving a space. So if I put the upper component as chi is going to be a spinner, 0, 1, or 1, 0, or 0, 1. So that tells you the spin of the particle. Then the lower component is forced to be sigma dot p over e plus m times chi. And since the equation there doesn't care about the normalization, we can choose any normalization. And my convention for this class is e plus m over 2e. Okay. Sometimes you see 1 over 2m's in that normalization, but it's a lousy normalization if you're going to deal with massless particles. So this is a much better normalization. Okay, if you work out then what this is, if I take u dagger of p, u of p, okay, that's just multiplying out those two things. That turns into 1. And if I just u bar of p, u of p equals m over e. Okay. Yes. U is a column. That's right. So here's the 4 components. 1, 2, 3, 4. Okay. Okay. The other solution is if I take psi of x is e to the plus I p dot x. Oh, actually, I should also say here that in this solution, p squared equals m squared. Okay, so that's the typical thing, which is, e squared minus p vector squared, the usual relation. Okay, we can find solutions that look like it with the opposite sign on the exponent. We call those v of p. There are also columns. The Dirac equation turns this into p slash plus m, v of p equals 0. Okay, so the sign on p changed. So instead of p slash minus m, it's p slash plus m equals 0. The explicit form of these, v of p, is same normalization. Chi sits down here, sigma dot p over e plus m. Chi sits up there. And again, v dagger v is equal to 1. Okay. So those are solutions. I have a useful relation that I'd like to write out. And here's the first case where you have to be a little bit careful about these things being column vectors and row vectors and all that stuff. So I'm going to write out what happens when I sum over m of u of p, u bar of p. So let's put an m index in there also. Okay. So the m index sits on chi sub m. Okay. And I'm going to use sum over m chi sub m dagger is, actually, sorry. Actually, that's not what I'm using. Actually, it's actually, for this I'm doing, actually I am. I'm sorry, let me, my notes have it backwards. Okay, first, what's that? Now remember, these guys are 2 component guys. And so, and I know what they are. They look like This is a direct, so let's write this how A and B is, so those are two component spinors. So the first one is 1, 0, A, 1, 0, B, and the second one is 0, 1, B, A, 0, 1, B. Okay, so here's the row vector, here's the conjugate. So if A and B were equal to the upper one, then this would be 1 and this one would be 0. If there's a lower one, then this is 1 over here, that's 0. This is equal to delta AB is what I wanted to do. Okay, which is it's like the unit matrix AB component. Okay, so there's the sum over m's. But now if I have u and u bar, these actually now are 4x4 things. So if let me put a label alpha there and a label beta on that one. So this is like alpha and beta run from 1 to 4. Okay, and so if you think of this guy being a column and this guy being a row vector, then this forms a 4x4 matrix with the index AB. Okay, so here's the first place we run into these things. Okay, so this is then the sum over m. Well, the two normalizations are the same. So there's a factor out in front that looks like that. And then it's chi m sigma dot p over e plus m chi m alpha, and then chi dagger m u bar is minus chi dagger m sigma dot p over e plus m beta. Okay. So if you think of this like a big matrix, the upper two components here are just the sum over chi's, which is like the 2x2 unit matrix there. And then the sum over chi's also work there. So let me write out what the next step is. So there's e plus m, or 2e. The upper two components is the unit matrix. I get minus sigma dot p over e plus m, sigma dot p over e plus m, and then minus sigma dot p squared over e plus m squared, alpha beta. So I take the alpha beta index of this. Okay. Let me work this out in more detail, just since it's unfamiliar to everybody. So here's e plus m, 2e. I'll factor out a 1 over e plus m, since that's sitting in various places here. There's 1 over e plus m, 1 over e plus m, 1 over e plus m squared. And I then get the top component is an e plus m, because that was 1 before. I get minus sigma dot p sigma dot p, and sigma dot p squared is p squared. This is minus p squared over e plus m. Okay. Alpha beta, and this guy I write in the following way: p squared is so this is minus e squared minus m squared over e plus m equals minus e minus m. All right, that's it. Okay, there. So this is all the little, I won't do this for everything, but let's. Okay, then my final claim is that this is 1 over 2e p slash plus m alpha beta component. Okay, you can sort of see it here. The top two components is there's a gamma 0 e plus m, gamma 0 e plus m. Then down here I had minus e plus m. So there's the plus m, and gamma 0 had minus 1 down there. So that piece is given correctly. And then this is gamma dot p vector. All right, so all that work turns that initial sum into this something that's pretty simple. Okay, likewise, sum over m v of p alpha v bar beta of p is 1 over 2m p slash minus m. Okay, it's technology. There's nothing deep there, but it does get you used to thinking of these things like matrices. Okay. If you're comfortable with that, we're then set to do quantization. Okay. So how do you go about this quantization again? Well, we're going to make these into operators. So psi is going to be an operator. And what you do is you sum over all possible solutions. So we integrate over all possible p's. We sum over all possible spins. We allow for some normalization, and then we put the solutions in. Either minus I p dot x u of p with a coefficient which we'll call b of p and m, and then either the plus I p dot x v of p, so there's the other solution, and a coefficient there which we give a name to, which we'll give it the name d dagger. Okay, so there's no sense that this is the Hermitian conjugate of that, so we give it a different name. Okay. So now there's a couple things we can do. So the logic can go either the following way. We can say, I'm looking for the commutation or anti-commutation rules that work for these to give me the right Hamiltonian, and so I can work out what it is. So the logic is either going to be the following. I will try out the anti-commutation rules, psi alpha of x, psi dagger beta of x prime at equal times, setting that equal to delta 3 of x minus x prime. And now I can work from there to the Hamiltonian equals, well, we'll see what it is, yes.
Should it be clear for us why you take the spin dependence out of U and V?
Well, actually, no, there is actually, those should also carry the labels. Is that the question? Yes. Yeah. So they also are labeled by M. Yes.
And the coefficients happen to depend on both the momentum and the spin.
That's right. So if you were just doing this classically, this is what you'd write, except you'd call that star. But now here we're going to try to make them as operators. And that's our starting nomenclature, and then we'll, of course, it's chosen to make these things the usual creation operators. Okay. So we could just say that when we did the non-relativistic field, we ran into this commutation rule for the fermions, so we're just going to keep it. That's one thing we could do and show that it has the right Hamiltonian. Or the logic could be the following: is you could invert, and with a little work you could see that B of P and M is the integral d3x e to the I p dot x. I want u dagger of P and M psi of x. Okay, so I could invert this, and then if I chose the anti-commutation rules for the B of P and M, equaling delta m prime times 2 pi cubed, delta 3 of P minus P prime. So if I chose the anti-commutation rules that I'd want, this then implies that psi alpha, psi dagger beta is delta 3 of x. Okay. So at this stage, I'm trying to just fill you in on the logic. Either we can impose the commutation rules that we want for the creation and annihilation operators, which we know that this is going to give us the right Hamiltonian, the right number operator, and show that the commutation rules follow, or we could just postulate the commutation rules and show that the Hamiltonian follows. Okay. The fact that they're equivalent just means it's all totally consistent. Everything hangs together. But that's what either of those pathways is there. Okay, but the answer is we want this, we impose that, and this comes out, and the other one I guess also I needed to do, d of P and M, d dagger of P prime, M prime, delta M prime, 2 pi cubed, 3 of P minus P prime. Okay. So whichever order you put the logic, that works out. I'm tempted to show that it works, but maybe I'll skip it. Okay. Let's just, the identities up above were actually needed for But let's just imagine we're doing this anti-commutator here. I don't know. People would like me to show you. I can show you a little bit of it, or all of it, the calculation. When I'm doing this anti-commutator, that turns into two anti-commutators. It turns into this one, B with B dagger, and it turns into this one, D with D dagger. And so the double commutators turn into integrals over these solutions. Okay, and I've got U in this, and I've got U dagger in this guy, and I've got V in this, and V dagger in the other one. And when you do that, these two relations that I derived up here are how you deal with that. Is you end up summing over the spins. These things just turn into this matrix, and the signs work out such that the U and the P's add up, and I don't know. It's a long calculation. Yes. Yeah. So the normalization constant, I actually haven't told you what it is yet.
No, in the two identities before.
The two identities, that should have been E. Was that your question? Yes, thank you, sorry. Those are the same. Okay. I don't know if I'm taking too much trying to skip the algebra. There's a bunch of algebra. There's a long, another page of algebra to get from these definitions down to showing that the commutator works out. The only thing that comes out of that is that when you do this normalization, there is chosen to be 1. Okay, so that's okay. So you can do. If anyone insists, I'll do it. The next thing that you do always, so we're just stepping through the quantization procedure. The Hamiltonian is then the integral d3x psi bar minus I gamma dot del plus m psi. And again, you plug in all those guys, algebra follows. And you end up with the following. It's a sum over m integral d3p, 2 pi cubed, h bar omega, which is omega p. And here's what you get. B dagger of p and m, b of p and m, minus d of p and m, d dagger of p and m. Okay, so I have to point out the minus sign there is important, of course. And I've done nothing with the order at this stage. Psi carries B in D dagger, and it's sat to the right in that equation. So this has got B plus D daggers in it. So here, the B sits on the right and the D dagger sits on the right. Okay. The trick now, of course, is this is in the wrong order to be the number operator, so I put it in the correct order. I use d of p in m, d dagger of p m is then anti-commutator is delta 3 p minus p prime delta m prime and 2 pi cubed times need. So this tells me that d dagger is minus d dagger d plus then 2 pi cubed delta 3 of 0. Okay, so after doing this, this turns into the right thing. The Hamiltonian turns into the usual stuff. So the Hamiltonian is sum over m integral d3p 2 pi cubed omega p b dagger b plus d dagger d. So the energies have the right sign. So that's the beauty of this construction. So all the energies are have the right sign, and then there's some 0-point energy for fermions, and for the 0-point energy for fermions is then, well, it's minus 2v integral d3p of 2 pi cubed times omega p. Okay, a couple of things. Here's the v. That's previously I told you how this thing turns into the volume of space-time. So that's why I wrote it as v. The minus sign comes from that minus sign, and the 2 comes from the 2 spins. There's a sum over m, and each of these 2 spins gives something. So this is the 2 spins. And the interesting feature is that it's less than 0, whereas the 0-point energy for fermions was greater than 0. So that falls out of the formalism uniquely. Okay. So that's the reason why if you do the right combination, if you have the same number of bosons and fermions, and if your masses were the same, then these would exactly cancel each other if you have, the right number of bosons and fermions. Okay, so that's supersymmetry. But otherwise, we have this negative 0-point energy. Okay, but the good news, the stuff that's really nice, is that the energies came out good. Okay. Last thing here, in this interpretation part, there's a conserved current, which is going to play a big role in everything we do. It's like the electromagnetic current. Okay. J mu is defined as psi bar gamma mu psi. So just take 2 of these spinors and put a gamma matrix in there. The conservation follows from the Dirac equation. So if I take I d mu j mu, So it's I d mu psi bar gamma mu psi. Okay. Well, the derivative can act on either the side of the psi bar. So let's just write out those two cases. It's I psi bar d mu psi. I'm sorry, d slash plus psi bar d slash, the derivative acts on psi bar there, psi. Okay, and I d slash on psi is equal to m, so this is equal to psi bar m psi, the first term, and the second one, if you look up what the formula was, it's minus m. So those guys cancel. So this is conserved. Okay. So there's then a conserved charge. Q is the integral d3 x psi bar gamma 0 psi, which is the integral d3 x psi dagger psi. So it's like the normalization integral that you have in non-relativistic quantum mechanics. And remember, since these are matrices, these indices are contracted here, so that's just the number. Okay, there's no leftover indices on that. And if I take dq dt, this standard derivation here, dq dt is d3 x d0 psi bar gamma 0 psi. But from the equation up above, it turns into integral d3x minus the derivative of psi bar del slash psi, so just the spatial pieces. And this is a total derivative. So this integrates out to 0 if there's no surface term at infinity, etc. So this is the usual proof that this charge is conserved. And if you write out what the charge is, Q, again, there's some algebra involved here because you plug all those solutions in there. There's B's and D's and B daggers on D daggers. It ends up being the following. It's the sum over M integral d3 p 2 pi cubed B dagger of P, B of P, and there's an M there, plus D of P M, D dagger of P and M, and we write that, we put that into the number operator, so you invert that, it's sum over M integral d3p, B dagger B, so this first term is the same, plus the second term is then D dagger P and M, D, P and M, and there can be some 0-point charge if you want. Okay. So this guy will drop, and one rationale for doing that, if you want, is that the universe is neutral, there's equal numbers of pluses and minus charges in the universe, so it drops out. Okay, does that make people happy? It's actually true. If you look at the standard model, the net charge, if you quantize all the fields, ends up being 0. Okay? I don't know if that's a deep statement or not, but that's a good reason to drop it here, so I'm not going to bother with it. Okay. So the interpretation. Okay. Yes. Please.
Do you get any other useful information or concept from the other components of the gamma matrix?
The spatial ones?
Yeah.
Well, it depends what you mean by useful information. Okay, so maybe the thing that would be useful in looking at this charge here, if you weren't interested in the spatial pieces, if I just put in a solution here. So let me just put in one of the solutions that we have of U's and V's. Okay, if I put in the U solution, as a 4 vector, that would look like U dagger U and U dagger actually U bar gamma vector U. Okay, so that's what we have there. Now remember, U dagger U was 1. So the first piece is just the normalization, which is sort of why this thing comes out to be 1 right here. Okay. The second piece turns into P over E, if you work out what it is. Okay. And I don't know how easy it is for you to see it. This gamma matrix has a sigma on the side, and and it connects the upper components to lower components. The lower component was sigma dot P over E plus M. And so the sigma times the sigma gives you just P back. Okay. I don't know, can you see if that in your head? Anyhow, this is what it works out to be. And so this is sort of like the charge is 1 and the velocity, this is the velocity. P over E plus M is the velocity. So this is very much like if I put a factor of the electric charge in front of it, this would be the electric charge and the current, Q times V of a single particle. So that's why it's a current. Okay. So that's the use of the spatial components, is that it shows you the flow, where these thing is moving to. It gives you the velocity. Okay.
So you have the 2 sources in the
Yeah. Yes. And so remember, when we do this as a field operator, the field operator really sums over all possible solutions. This was it for one solution here. And then when I integrated over x, I got the 1 here. If I had taken the integral over the spatial components, I would have had P over E sitting here for this. Okay, that's what I would have gotten. And in principle, it contains all the possible solutions. It's the integral over all these solutions with the creation operators, P over E. So then its matrix element, if you take its matrix element, it gives you P over E once you take the matrix element. Okay. So actually here, that's what I'm trying to do next, is let's define, let me call it F of P, the state, which is taken B, has a label M, B of P, B dagger P and M acting on an empty state. And if I define F bar of P and M as D dagger P and M acting on the empty state. Okay, and then since Hamiltonian and the chart, this Q, involved in the number operators, we would end up with the Hamiltonian on f of p and m is omega p f of p and m, and q on f is 1, it's plus 1. And the Hamiltonian on F bar was also omega p. And the charge on this guy is -1. So the outcome of this quantization procedure is all the particles' energies are positive. But they differ on this charge, and that's the Q is the particle number charge. So Q is +1 is the particle, and the other is the antiparticle. Q -1. And if we multiply by the electric charge, it will be the electric charge of these guys is, say, positive, and these guys is negative, or vice versa, depending on the sign of the charge. So these, they always carry positive energy, but they carry some opposite charge, okay, which will be electric charge too. Okay. Any questions about that? So the main thing is we've got particle-antiparticle pairs coming out with positive energy. This, you know, if you go back to your quantum mechanics and you look at solutions that look like this, in quantum mechanics that's always called positive energy. Historically, when you put a solution like that in, that was confusing. That looked like it was supposedly negative energy. Okay, just because you flip the sign, it's either plus I, E, T. But that interpretation is wrong. If you go through it, they all have positive energy. Okay, so that looking at the sign of the exponent and calling that the energy is not right. You have to calculate the Hamiltonian, and this Hamiltonian works out just right. So it's really the more beautiful way to think about things. Okay, questions? Last thing I have to do for this is I have to give you the Feynman propagator. And there's just a few little wrinkles associated with this. Okay, here the Feynman propagator, which we'll end up using in perturbation theory, is x minus x prime. It's traditionally called S for the fermions. I have no idea why. It's defined as 0, time-ordered, psi of x and t, psi bar of x prime t prime, vacuum. But again, these guys are vectors, or these have components. And so if I put a component on this called alpha and put a component on that beta, then SF has these two components, so it's like a matrix, a 4x4 matrix. Okay, the other wrinkle is that time ordering is slightly different. Time ordering of psi alpha, psi bar, beta is if, alright, so let's make this x prime. If x is bigger than x prime, it's the usual psi it's the usual ordering. And then if x prime is bigger than x, it's the reverse ordering, psi bar beta of x prime, psi alpha. But there's a minus sign right there. Okay, I save that for the end. And that's just because these fields are fermions, and so if you flip the order, you pick up a minus sign. So that's the choice. It's part of the definition of this, because that's how it arises in applications. Okay. SFX, the Feynman propagator, is a Green's function for the Dirac equation. If I take I del slash x minus m times ISF all right. Now that's, again, it's a matrix equation. So let's be a little careful. Let's make it alpha prime, alpha, alpha beta. Okay, so summed over alphas, that's repeated index. So it's matrix multiplication there. Okay. So when this derivative acts, it can either act on psi, which carries the label x, or it can act on the time ordering. So there's two pieces. There's one piece which is 0 time ordered id slash minus m psi bar. And the other one, okay, that one, of course, I'm going to set equal to 0. That's by the Dirac equation. Okay, right? And but the other one, the time derivative can act on the time ordering. So I get I gamma 0 from zero. I get delta of x 0 minus x prime 0 psi dagger plus delta minus delta x prime 0 minus x 0 psi dagger psi. But it becomes this becomes a plus because there's two minus signs. One is the derivative on the theta function is minus, and there's that minus there, so it becomes a plus, so it's minus squared. These give you equal times. This gives you the equal time commutators. And one of these is barred. Sorry, bar. The equal time commutators give you three spatial delta functions. This turns into the I delta 4 of x minus x prime. Okay, so it's the Green's function. Yes?
Why is not finding the
Yeah, okay. Let's, all right, so this is alpha prime alpha alpha beta, and this is alpha prime alpha alpha beta alpha beta. Okay, and this is then delta alpha beta. Okay, the okay. The other thing I've been slipping past you a little bit. You remember the commutators of psi with psi dagger gave you a delta function. This is psi bar, so there's an extra gamma 0 floating around. This gamma 0 times that gamma 0 gives the unit matrix. Okay. Gamma 0 is the unit matrix. Yes, that's where it went to. So gamma 0 was 1 minus 1. So you square that, that's 1. Okay. All this technology. All right. I'm trying to get our pass through it without dwelling too much on that, but I guess we have to. Okay, so it's the Green's function. It's a matrix equation, which you normally wouldn't write that out. You just say I d slash minus m sf is I delta 4 of x minus x prime, where all the matrix stuff is implied that this is the unit matrix. That's the 4 by 4 unit matrix. Okay. So then here's the solution. The solution is SF of x is integral d4p 2 pi to the 4th p slash plus m over p squared minus m squared plus I epsilon e to the minus I p dot x. Okay. And let me just write this in the form you normally see it. It's the integral d4p 2 pi to the 4th 1 over p slash minus m Okay, this notation here is a little ambiguous if you think about it. Remember, this is a matrix. These are gamma matrices. So 1 over p slash minus m. P is a 4 by 4 gamma matrix. M has a 4 by 4 unit matrix in it here. This is a matrix, but this is just the definition of what this is here. We'll see in just a minute that if I do, let's write out p slash minus m, p slash plus m. Okay, that's p slash minus m squared. Okay, right, the cross terms cancel. That's equal to, well, that's going to be p squared minus m squared, and I'll just do the proof over here. Any a slash for anything is 1/2 a mu a nu gamma mu gamma nu. Right? A slash is gamma, A contracted with a gamma matrix. So I've just written this, That equation is the fancy equation, 1/2 a slash plus a slash. Everyone agrees on this one, and this is just that equation. And then, since that commutator is 2g mu nu, this just turns into a mu, which is what we mean by a squared. Okay, so this second form here just follows by using this identity p slash minus m, p squared minus m squared. Sitting here, we've written as p slash minus m, p slash plus m. The numerator cancels. You're left with that. And then the last thing I needed to show is if I take I d slash minus m sf of x, well, that's an integral d4 p 2 pi to the fourth. Well, the derivative brings down a p slash, so it's p slash minus m times p slash plus m, p squared minus m squared. Okay, by doing that, these guys, by that identity that I just showed you, just become 1. And this equals then delta 4 of x. Okay. All right. I guess I'm going to stop there. Let me take questions if anybody wants to ask questions. We're through the introducing the fields part section now. Next time we come back and we start talking about interactions, the very first thing I do is QED. So we're going to set up QED next time, quantum electrodynamics, all the interactions for either charged scalars or charged fermions, and then we'll do some other theories, interacting other theories too. Okay? Good. So that should be more fun than this review stuff. Let's